Hello everyone, good evening. Could someone please confirm is my audio is clear?
Yes, sir.
Oh, hi Sudhir.
Yeah, audible, sir.
Thank you. We will wait for a couple of more minutes to allow everyone to join and then we'll get started. So, good evening everyone. Thank you for being on time. I am Sourav Goswami. I am a PhD candidate here at IIT Bombay in the Department of Mechanical Engineering. I primarily work in the broad area of additive manufacturing. I'll be your TA for the course Fundamentals of Additive Manufacturing Technologies. Could someone please confirm if my screen is visible?
Yes, sir. Visible.
Thank you. Thank you, Sudhir. Just a moment. So let's get started. Welcome to the first live session. The instructor for this course, as you are aware, is Professor Sajin Kapil from IIT Guwahati. I am Sourav, joining from IIT Bombay. These are the fine points we'll be going over today. So we'll be introducing ourselves to each other. We'll have a quick recapitulation of the lecture notes that were shared for this week. Then we'll solve some sample problems, which will give you a better insight into the course, as well as, I hope, help you with the assignments. And just some quick points. So during this session, if you want to communicate with me, please raise your hand and I will notice and I'll ask you to unmute and then please speak. Otherwise, I'll request you to keep muted during the entire session to avoid any disturbances. And I gave a brief introduction of myself. So could some of you introduce yourselves, what you're doing, and what is your expectation from this course? Just feel free to unmute and introduce yourselves. Sudhir, could you start?
Yeah, sir. Myself, Sudhir. I'm working in AJ Institute of Engineering College, Mangalore, and presently doing a part-time PhD in NITK, Surat, sir. So, as a part of coursework, so I'm opted this course, and my research area, so maybe in the 3D print.
Okay, and will these course credits count towards your coursework?
Yes, sir, sure. It's a 3 credit course.
Okay. All right, Sudhir, thank you. Anyone else volunteering to introduce themselves and state their expectations from the course?
Yeah, good evening, sir. My name is Presley. I'm actually a first year PhD student at NIT Calicut, and I am presently planning to work in the field of additive manufacturing, especially in wire arc additive manufacturing. So, to gain some fundamental knowledge about this additive manufacturing, I have joined for this course. Thank you.
Thank you, Presley. I hope the course does you well and it is able to help with your research.
Okay, yes, sir. It's going on well. Yeah,
Thank you.
thank
So we'll get started. First, I would like to give some bird's eye view of additive manufacturing in India and why should we actually care about it, apart from research, of course. Research gives us a very concentrated view. We are often limited and we often miss the big picture. So on your screen, you will find is the metal additive manufacturing size of the market as it was in 2021 and as it is projected to grow. As you can see, it goes from 2.5 to 11.45, so it grows 4 times. And we might just be able to contribute to this growth, especially when you look at Asia. Okay, is this right? Especially when you look at Asia, you see that China and Japan have cornered most of the market. The share from India is less, it's anywhere between 3 to 5%, but we are gaining ground. A recent report which actually highlighted the most number of publications as well as the most impactful publications in the broad field of AM suggested that among all the international institutes, the National Institutes of Technology and the Indian Institutes of Technology did have a good foothold. Of course, NTU was leading the charge, followed by a few Chinese colleges. And if we were to see the end user of the metal additive manufacturing market, currently you will see that it's more or less evenly spaced between aerospace, the automotive and healthcare sectors, and some other niche sectors. Whereas by 2031, that is, say, in the next 7 or 8 years, aerospace, of course, will grow, but so will healthcare by quite a big margin. That is why you'll find that a good chunk of AM research is dedicated to healthcare, biomedical implants, and other in vivo and in vitro related applications. So for recapitulation, I'll refer to Professor Kapil's slide. You must have already gone through them. And the first lecture was on, of course, an introduction to additive manufacturing. We looked at a few of the common terms which are actually used to refer to this process. Among them were 3D printing and stereolithography. Additive manufacturing, of course, the most commonly accepted. Layer manufacturing, because by definition it is a layer by layer uh, process. In fact, if some process is not layer by layer but fulfills all the other criteria of AM-like processes, it will not be counted as one. Solid free-form fabrication, of course, another common term often encountered in literature related to AM. We have digital manufacturing and rapid prototyping, perhaps the oldest term used to refer to this. And as Professor Sajan explained, that in 3D printing, we are doing nothing extra. We are just adding another axis, which is along the z-axis. That actually helps us to create objects in three-dimensional space rather than simply printing them on a piece of paper. Of course, when I say the z-axis, it can either be given to the build platform itself, as in the platform moves in the z direction, the deposition head moves in x and y, or the stage can move in x and y, while the head moves along the z direction. Both are possible, both are commonly observed. Here we have a formal definition of additive manufacturing. Now, the key terms to look out for are, of course, layer by layer fabrication of three-dimensional physical models directly from a computer-aided design. This is necessary. It is an automatic process used to manufacture parts, prototypes, tools, or even entire assemblies at one go, directly from their CAD models without any cutters, tools, or fixtures. Now, this is controversial because, of course, you need some degree of post-processing to it. But still, I would say till the manufacturing stage, it is free of any sort of subtractive processes. And of course, more importantly, any such process is actually independent of the object geometry. Now, where this helps is irrespective of the complexity of the geometry or the difficulty of the material. For example, superalloys such as Inconel, they are notoriously hard to machine, but to deposit them via additive manufacturing is far, far easier. You can print the most complex geometry with Inconel and yeah, you'll have your part. This is where AM actually takes the cake and is actually superior to most conventional manufacturing processes. Here again, we see the three broad steps of an AM cycle, which is the pre-processing stage, where you sit at a computer, you design your CAD file, visualize it, correct for errors, you tessellate it. More on this in the upcoming slides. Slice. Slicing is what is done by most of the common software, such as Fractal or CUDA. You check for support structures, generate them if needed. If not, well and good. Second stage is the manufacturing or the printing itself. And then, as we were discussing, the post processing, because the part that we have here, it might have support structures, or it might have even chemical segregation, or it might have poor finish, that is surface finish. And all of these things can be taken care of by the relevant post-processing methods. Again, why support structures are required? So in the diagram to your left, you'll find that certain parts of this structure have an overhang angle. So basically, when you're building this wall, there is nothing beneath it for supporting. What will support its weight? Now, this is not needed when the angles are tolerable. Of course, when you're depositing something right on top of the other, it's okay. Something slightly off might still work. But what is this extent? What is this limit? This, and as we continue building, this overhang, that is this angle with the vertical axis, is what defines whether we'll need a support structure or not. If this angle is shallow, say somewhere here, maybe a support structure is not required. However, beyond the critical angle, definitely you will need support structures. Now, we were discussing some areas in which AM is absolutely necessary and where it trumps conventional manufacturing processes. And one of the reasons is that it can address the need for customization. I think the earliest example is from patient implants. So implants are highly patient specific. An implant which is designed for your body might not fit mine. But to have a reliable manufacturing method which accommodates such vast variation in dimensions in design requirements at a feasible cost, this gap was filled by additive manufacturing, increased product quality. Now again, often we keep hearing that additively manufactured parts have defects, pores, for example, and low densities. They can also have chemical segregation. So what is this increase in product quality that they talk about? We'll find out later in the course, and a faster response to market. So with an additive manufacturing setup, you are future proof. You don't need to overhaul your entire assembly line or your entire manufacturing unit just to adapt to, say, a change in design guidelines or a change in the prevalent technological standards. And as highlighted here, generation of the STL file and actually manufacturing the physical objects are maybe two of the key aspects which we will concentrate during this course and mostly during our research as well. People related to the field of additive or working in additive will often hear the term STL. I mean, of course, all of us during our CAD CAM classes have, and it is one of the more commonly used file formats for exporting 3D objects, along with, say, some of the older ones like IGES or STEP. But when it comes to AM, STL is the predominant standard. It has legacy support, and it stands for, well, first stereolithography. That is where, in fact, it came from. Next, it was expanded to mean standard tessellation language. and also called standard triangulation language in some literature. What is special about this STL format is that it uses a series of linked triangles, linking is important, to recreate or reproduce surface geometry. So what you're getting is actually a surface model. It's not a solid model, it's hollow. The more triangles used, the higher the resolution of the 3D model. So it's like discretization of the surface. Similar to what we do in a finite element analysis. We break our domain into discrete areas or nodes where we solve our governing equations. And with proper continuity between the neighboring nodes, we have a solution that fits the entire domain. Now, STL is widely used mostly because, yeah, it's simple, light, and easy, and it has legacy support. On the right here, we have examples of how slicing can affect the final outcome of a 3D printing process. So slicing is basically dividing anything into slices or layers. The intersection of these slicing planes with the 3D geometry generates certain profiles, and it is those profiles which are printed in each layer, such as you have on the right. So maybe this is layer 1, layer 2, 3, 4, 5, 6. Notice that you are missing some material in here. This was supposed to be a curve, but rather here it's more like a staircase. These are the sources of errors in AM. This is called the stair stepping effect or the staircase effect. Here you see that the same complex geometry of a rabbit, when it is sliced into thicker layers, it will print fast, but as you can see, it is not actually capturing the exact geometry. It is coarse. However, when we are slicing it using very thin layers, the geometry is reflected well. It is able to catch most of the complex geometry. However, the print time will increase exponentially. So what is needed is actually something called as adaptive slicing, where the geometrically less complex parts are sliced into thicker layers, whereas the more intricate bits, such as these curves over here, we use fine slicing for such regions to capture the geometry more accurately. Here the flowchart actually depicts the difference between virtual prototyping and rapid prototyping. So rapid prototyping is where you are actually generating a product. It might be a scaled version, it might even be full scale, but it's a prototype. Whereas virtual prototyping exists only in your computer. It's a CAD model. You can simulate with it. You can run some simulations. You can predict what will happen to the part, but then it's all predictions. It's not validated as of yet. This is a flow diagram connecting virtual prototyping with rapid prototyping, connecting these two concepts together to generate what is called rapid manufacturing, that is the entire manufacturing cycle. Now we'll quickly go over some of the capabilities of AM. They are divided into geometric capabilities and material capabilities. Here we have a hinge assembly. Now to the left, you see what may be actually produced via a conventional manufacturing method. So you have these number of parts, at least 5 mentioned here. You manufacture all of them separately. You have separate manufacturing lines, say for this small part here, for this one, this cylinder right here, and you assemble all of them together. Of course, standardization, geometric dimension control tolerances will play a part here as to how well they assemble. On the right here, you have not the same, but something of similar functionality, a part manufactured by additive manufacturing. Why are they not the same? This is because of something called design for additive manufacturing or DFAM. So when you have a product and you already have a established design cycle for it, which enables its production through through conventional manufacturing processes. The same cannot be always directly adopted to an AM framework. Often you need to make certain modifications in the design, improve them in some places, or simply make them more convenient, more printable by a 3D process. But what you must not compromise on is the functionality in terms of, say, the degrees of freedom, say, the strength of the final component, the expected life. Such assembly cannot be made by any conventional manufacturing process in a single go. However, with an additive process such as FDM here, this is a one-step process. You just print it, take it off the plate, maybe snap some of the supports, and you're good to go. Again, another capability which is highlighted here is the conformal cooling channels which can be built in. So usually, as was also pointed out in the lecture, in any conventional process, what you will have are such symmetric or rectilinear cooling channels. You will have the liquid going in from one side, coming out the other. But this does not actually take into account the actual intricacy of geometry of the part that you're trying to cool. Mostly because it is time consuming, costly, maybe even difficult in certain cases to achieve this. How do you actually build a channel which goes around this part, comes back out again, like here, and does so around all of it? Now, this does not have a prismatic geometry, does it? The cross sections are changing. But with AM, we can because what we are printing is essentially only one layer at a time. So in a certain layer, we can print the cooling channel as we wish. Maybe in this region, you'll not deposit any material. You'll have material here. In the next layer, where the cross section changes, maybe you'll not deposit material over a smaller region corresponding to say this. You have material over the rest of the places. So conformal cooling channels is one of the major applications of additive manufacturing. Now, of course, mass customization. So in the same print cycle, you're printing such various geometries. Hardly any two geometries are alike. This is a set of keys, as you know, they're all supposed to be dissimilar. And yet each one can be printed just as precisely as expected. And assuming that they have the same height, all of them will be finished at the same time, and you have scope for unlimited customization. Here on the left, we have something called lattice structures. So lattice structures are mostly composed of what are called, say, repeating cells. You have a unit cell with a well defined design. Say I have an hollow cube, something like this. So only the walls, like a wire frame, but nothing in it. And then this repeats over and over unless you have a volume. Now, even in the lattice structure, you see that there is dissimilarity. So here in this region, it is more porous. So the cell sizes are larger, they are less dense compared to say somewhere on the periphery here, where you might even observe some closed cell porosities. But all of this is easily achievable via AM. On the right, we have an example of the human bone. Again, this is an example also of a functionally graded material because on the outer periphery, the bone is hard as well as it is dense. Whereas as you go inside towards the radially towards the center, what you have is a decrease in hardness and a decrease in density. Similarly, such structures can be achieved via AM via a very well-defined design. Say you want to proceed in space where you want the porosity to decrease 10% for every 10 mm. It can be done. Here are some of the materials which are capable of being processed by an additive manufacturing setup. We have polymers and composites. A lot of work has already been done. It is well established. Mostly the technology which you would have heard associated with polymers are FDM, which is your desktop 3D printers, as well as say VAT photopolymerization, where you have a vat of liquid and a UV laser to cure it. We also have ceramics. At IIT Bombay, we have a ceramic 3D printing setup. It is somewhat similar to a VAT photopolymerization construction. Now, 3D printed homes are all the rage. In IIT Madras, they have full-fledged 1 BHKs as well as security guard rooms that were actually 3D printed on campus. Similarly, in IIT Guwahati, there is a great volume of research dedicated to 3D printing using concrete and cement, biomaterials and food. Food 3D printing is an interesting concept that I came across, and they use these biocompatible nozzles for printing food. Say these can be used for extruding cream or dough or the like. And you can have these very beautiful, intricate patterns which are otherwise difficult to achieve, as well as, of course, customized food. A very interesting application. Metals, of course, mostly I work with metals, metal alloys, high entropy alloys, magnetic alloys, yes. In fact, it is also possible to manufacture components using additive manufacturing technologies which have a variation in magnetic properties along a chosen direction. So FGM with a variation in magnetic properties have been made. Here you have an example of a functionally graded material. So the tip of the spacecraft is subjected to very high temperature as well as extreme service conditions. It can go suddenly from a highly oxidizing environment to vacuum. It is subjected to a lot of viscous drag and friction. And so what can be done as a strategy is to say coat the tip with ceramic. But we know that coatings are fragile as well as costly. Now they have a very limited lifespan and they may also come off. So an alternate strategy is actually to rather coat. Why not incorporate ceramic materials in the bulk itself? So why not make a part that is partially ceramic, partially metallic, and strong all the way through? Now, why not all of it is ceramic? Because you want your body to be light. It's an aerospace structure, so it has to be light yet strong. It has to be durable. It should have a certain degree of toughness, whereas ceramics are hard and brittle. But ceramics are important in the outermost regions because they have good heat resistance and oxidation resistance. Now, what becomes critical is actually this interface between the metal and ceramic. And often it is phenomena occurring at this interface that govern the performance of such functionally graded parts. Of course, it's not a sharp interface, rather it's diffuse. You can see a region across which this transition is taking place. It can be gradual, or I mean, this is more like the ideal case. More realistically, your composition will vary something like this because there are dilution and other effects coming into the play. And this interface is also the region where you'll observe most of the defects, say cracks or lack of fusion pores. Here again, we see a colorful object. Now, what should be noted is that this color is not applied externally, rather, these parts have been printed with different colors of filaments. So, say green, yellow, red, this is blue. And even then, you have different colors of blue. So, maybe I'll mark one. So, this part has been printed with at least five different filaments as per necessity. And you can see that the transition is really smooth. And they have the same color throughout, as Professor Kapil noted in his lecture, because the colors are not externally applied, they are the material. These are some other examples. On the left, you have a optically transparent object. On the right, something colorful. ASTM classifies additive manufacturing into seven broad processes, and these are, of course, uh, defined on the basis of the setup, on the basis of the feedstock that they use, as well as perhaps more importantly, the energy consumption of the process. And as you would have noted, energy increases as we go further down this list. Up here we have vat photopolymerization. This is the vat. It's a tank full of liquid. This liquid is usually a resin, which is photosensitive. So if you leave it exposed even to ambient light, it can get cured to a certain extent. And here you have an energy source, mostly a UV laser of very low wattage, which is shown across the entire bed through the movement of this mirror, and which cures the material one thin layer at a time. Say in the given layer, this is my only area of interest, this little region here. So the laser will cure this region. Then in the next step, the bed will go down by a predetermined height along the z-axis, and then the next layer will be cured. Here we have material jetting. So as the name suggests, the material itself is deposited in the necessary regions, and it is accompanied by a energy source which cures it. Contrarily, in binder jetting, it's not the material, but rather it is the binder which is deposited on top of the material which is already here. Say it might be in the form of a bed full of powder. You have layers of powder, and you're depositing small droplets of binder onto that powder. Wherever that binder falls, the powder gets uh, say not compacted, they get attached, and through these adhesive forces, they form what is called a green part. This green part must later be sintered to actually release the binders and to have a strong object. Material extrusion is perhaps the most commonly observed example. This is what is used in fused deposition modeling or FDM. Here you have an example with two nozzles, and there can be more. Uh, One can be used as the build material, the other may be used for support material, or both may be used for build material. It's totally up to the user. This nozzle right here, it has a resistance heating which mostly goes up to say to the order of 250 degrees Celsius. So, and you have the a roller mechanism actually pushing the filament into this heating chamber. So the filament is pushed into the chamber with certain force. It is melted, and a molten or in certain cases semi-molten uh, filament is actually deposited on the layer. And of course, as you can notice, the scanning speed, that is how fast this head moves, it also play a key role because what you're depositing is, say, a semi-solid trail of liquid. So if you go too slow, you end up overbuilding in the same regions. If you go too fast, maybe you miss certain regions. Sheet lamination is very interesting, but sadly with less application compared to the others. In this case, your feedstock is a sheet which you roll onto the bed. So maybe traveling here, unrolling from your stock, you machine it. So there are two strategies here. One is called form, then bond. We are actually making the shape on the sheet and then detaching it and then joining it with previously deposited layers or previously prepared parts. So maybe you have a stack of them and then you join it on top. The other strategy, which is called bond then form, is where you're actually first stacking up these sheets. So you have many of them, and then together you start to make out your shape, maybe with some abrasive cutting, maybe with a mechanical cutting, whatever means. You machine this through all the layers, and then you end up with your finished part. So these are the two design paradigms. In this, sheet lamination is also more formally called as laminated object manufacturing or LOM. Powder bed fusion, perhaps most widely used for, I will say exclusively used for human implants. You have good surface finish, good dimensional control or accuracy. However, low deposition rates, so maybe I can call these pluses. On the negatives, you have low build rates, wastage of powder to a certain extent, even though strategies are evolving to utilize or reutilize the powder in the bed. And the build volumes are relatively small. In this case, somewhat similar to wet photopolymerization or even binder jetting, you already have a bed which has powder. When the previous layer is centered, a new layer will come via this, say, coater. It can be a roller, or it might also have some a more prismatic geometry. This coater brings on a new layer of thin powder on top of the existing surface. And again, the region of interest will be centered. The powder in this region will melt partially, will bond to each other, whereas powder in the rest of these region will remain as loose powder, which can be easily removed later. And at last, we have directed energy deposition, perhaps the most energy intensive process. However, it is also the most industrially scalable. In fact, if metal AM is to have any future in the industry, it will be through directed energy deposition only. Large build volumes and deposition rates. Also, printing multi-material parts is easier compared to, say, powder bed fusion. However, the downsides are that dimensional accuracy is maybe worse, not too bad, but definitely worse than some of the other processes. Environmental control, though, I mean, it's the same chamber as in PBF, but because of the larger chamber sizes, often controlling the environment of the chamber is more difficult than in a powder bed process. Also, this process is more prone to defects, or the defects have a more debilitating influence on the properties of the final part. Again, as Professor Kapil mentioned, that we go from wet photopolymerization to directed energy deposition along increasing energy. Typically in DED setups, we use lasers north of the range of say 2 to 6 kilowatts. Even more powerful setups are coming up. Whereas in wet photopolymerization, you have the order of milliwatts only. For powder bed, something like 500 watts will get you through most materials. And here is an alternative classification based on the type of raw stock. Interestingly, there is no gas AM yet. I have come across a couple of proposals which did pitch this idea. They have not seen light of day yet, but yeah, it's a really interesting concept. In fact, I actually am aware of certain nano additive processes which use an aerosol. So technically not a gas, but yeah, close enough. For additive manufacturing, they build these really intricate nanostructures that brings us to the end of the recap for lecture one. We'll now look at some questions. So I will really appreciate if you guys answer along with me, and you can unmute freely and answer. So the first question which I have here is functionally graded materials or FGM may have variation in which of the following properties? So can FGMs have variation in density? Can someone please answer? Okay, someone is saying D. We'll go step by step. So yeah, FGMs can actually have variation in density like we saw in the example of human bone. So this is there. Please note that the questions can be multiple correct type. Can FGMs have a change in or a variation in material composition? Can you actually build? Okay, Priestley says A and B. So can you actually build a material, say something as simple as a cube, which has material A at this end, material B at this end, and maybe some A plus B here. This is 100% A, 80% A, 50% A, 50% B, and you have don't know, maybe 20% A, and finally you have 0% A. Similarly for B, this is 100% B, 80B, 50, 20B. So yeah, it is possible. So it can have actually a variation in material composition. Porosity, true, because often density is decreased by adding porosity. And as some of the students have already pointed out, the change in mechanical properties can also be achieved. So all four are correct. What is the feedstock material for a directed energy deposition process? Would someone please volunteer to answer? And feel free to unmute, you need not type in the chat. Akhilesh Singh, are you with us? Okay, no volunteers. So in a DD process, have you seen powder being used? So I think the most common, yeah, is someone answering? Karthik?
Sir, wire method?
Sorry, could you please repeat?
Usually powder.
Okay,
Yeah.
so I have a vote for powder. Anyone saying filament?
So I think so. It is answer D, wire.
Okay, I have a vote for wire. Anyone saying filament? No. Anyone saying liquid? No. Someone mentioned powder. So often the most common imagery you will see is there's streams of powder coming in coaxially, say along 6 holes in the nozzle and getting concentrated at a point. And this is where you're getting deposition. But some of you might be aware that just like powder can come out of these nozzles, so can wire. In fact, these days, the most common design actually involves annular lasers or discrete lasers. So you actually have these holes are actually the output for laser, and in between you have either so coming out of you towards the board, either wire or even multiple wires which meet the laser. So say this is your stock of wire or powder, and these are the laser beams. They meet at a certain standoff distance and they get melted and deposited. And of course, as someone pointed out, powder. So both A and D.
Sir,
Yes, Karthi.
second question, I have doubt, sir.
Yes, Karthi, please say.
Direct energy deposition process means only wire only to come, na, sir. Powder means powder means it is powder deposition like this it will come, na, sir. Powder
Uh,
energy deposition. That means SLM, DL, DMLS, like this only powder. But direct energy method only wire only come, na.
no, Karthi. So actually, when you say directed energy deposition, it can actually have both powder and wire. So in SLM, SLM is short for selective laser melting. SLS for selective laser sintering. Both are actually what we call as powder bed fusion processes, where you have the powder laid out in a bed. It is brought in by a roller, and just the energy beam, say a laser or electron beam, it scans over the surface and it sinters your region of interest. In directed energy deposition, you have the energy source as well as the material coming onto the surface. When you start, all you have is the substrate. TD can include WAM, it can include laser DED, can include E-beam DED using wires only. But yeah, it can have wires. Maybe in the next lecture, I can share a few videos where they are depositing wire using DED setups.
Yes, thank you.
Thank you, Karthi. Any other doubts?
No, sir.
What is the wavelength of laser used in a VAT photopolymerization process?
Ultraviolet.
And the question is asking not for the exact wavelength, but more like the range.
Ultraviolet.
Did someone attempt an answer?
Ultraviolet.
Yes, thank you, Akhilesh. It is ultraviolet indeed. This question is actually asking us to compare additive manufacturing and conventional manufacturing processes. We have a few statements regarding both of them. The first one is that additive manufacturing can fully replace conventional manufacturing. Is this true? Please focus on the word fully. So the thing about AM is that it does offer many advantages, such as complexity of shape, the ones we discussed, and rapid prototyping, then a large material library, So anything from ceramics to polymers to metals and whatnot, food. But it also has a lot of capital investment or cost, both initially as well as during running in terms of the feedstock. Then it is highly energy intensive. And when you combine these two along with the necessary skill to operate a DAT setup or any AM setup in general, what these end up doing is drive up the price. I mean, you go to the market, you want to buy, say, a couple of screws. Do you want a very high quality printed by AM, made of some titanium, which costs 500 rupees a pair? Or do you want your regular screw, which is, made by some conventional on a lathe, threaded, made of steel? Of course, cost dictates everything. So can it ever fully replace conventional manufacturing? No. Are conventional manufacturing processes superior to AM? No. Can they actually make lattice structures? No, they can't. What is true then? Additive manufacturing is actually complementary to conventional manufacturing. So the root here is that you identify your need and of course your budget, and then evaluate which process to opt for. For steel, maybe you can cast it. It will be cheaper if it's a simple enough shape. For Inconel, if you cast it, the lave phases or the deleterious second phases, they will annihilate your part. It will fail prematurely. Again, you cannot machine Inconel. So in that case, maybe opt for an AM. If the part has very intricate geometry, again, AM. If you need a lot of them, thousands maybe in a short period of time, maybe opt for a conventional process. So they are complementary. None is superior. Which of the following may be classified as AM? So DED definitely. I mean, we spoke so much about it. What about lithography? Would someone please like to attempt? In lithography, you have a substrate, you have a layer of photoresist. It is then exposed via some energy. Yeah, I see a layer, layer by layer. I see some energy. I see a substrate. Looks like AM, but is it AM?
No.
Okay, Shiva. But what reasoning can we give to classify it as not AM? What is so contradictory?
Because there is no material deposit.
Why not? So you have this layer of photoresist, and when you
Mhm.
expose it, you are selectively removing some parts. So this part is gone. This part is gone. So yeah, this is deposited, right, on your substrate.
Okay.
Because it is not layer by layer.
Okay, so say I want to build a next layer on top of it. I deposit another layer of photoresist. I do the same process, maybe again deposit here, 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 do it again and again. So it is layer wise. Alok, we are trying to figure out why it is not additive. I mean, what disqualifies it? When you say completely, what is missing or what extra are we doing which is not so additive like? Okay, maybe look at this definition. So this is from the ISO ASTM standard. It says that additive manufacturing is the process of joining materials to make parts from 3D model data. Yes. usually layer upon layer, true, as opposed to subtractive manufacturing and formative manufacturing methodologies. So the moment a process has a subtractive step where you're actually removing some material, like in laminated object manufacturing, you do. Okay, yeah, Karthi has the right answer. So chemical machining. It is because of this subtractive step where you remove this exposed part via a chemical machining process is because optical lithography is not an additive process. The third one, investment casting, is easy to classify. I'll leave that to you. So we spoke a little about support structures, and again, a quick recap. When you have a structure which has these overhangs, which basically implies that unsupported parts, you need to give it supports. So what can be a viable strategy to actually avoid these supports? I understand that we should not change our geometry. I mean, if I want to print a inverted funnel like this, I cannot just make it a cylinder just to avoid printing some extra supports. So given that the design remains constant and cannot be changed or compromised, what other strategies can we have? Modify the design? No. Alok says B. Okay. Sudhir also says B, right? So maybe we can orient it in a way rather than printing it like this. If I print it like now, you see, there is no part which needs support. It is self-supported. So a good orientation or a preferential orientation, true. Stronger material, I don't see how that changes anything. Can someone tell me why using a stronger material will not eliminate the need for supports? Say I was printing this with polymer and the software tells me that I need supports. So what I do is I go and print it with Inconel 718. Will it still need supports? Someone please. Will changing the material eliminate the need for supports? No, right? Because it's a design constraint. It's not a material constraint. Even if I were to print the same object or the same 3D object with a metal or something even stronger, it'll still need supports. It is not dependent on material properties only. Thank you, Alok. That is correct. Use a build platform with higher degrees of freedom. So rather than have a platform which is flat, if I were to tilt my build platform such that this part which had a large angle with the vertical suddenly becomes straight. Is this a viable strategy? Tilting the bed? It is right. Because now you see this region does not actually, it is not unsupported anymore, or it does not have a large inclination with the vertical. And say if you retrofitted an AM setup into a CNC, which has say anywhere between 4 or 5 degrees of freedom, the bed itself can eliminate the need for any support structures. So both B and D are correct options here. This one I think we already discussed. In what scenarios would AM be preferable over conventional manufacturing? When you have low volume and high customization, yes, I need a low number of parts, but I need them to be very design specific, very consumer specific. High volume, low customization, no. I will never meet my targets. It takes a lot of time. As well as they have low customization, so maybe they are easy shapes. So why would someone not opt for a conventional process? Complex shape, lattice structure, yes. Low production cost, as we discussed, AM by default is a high cost setup as of now. It is the costs are going down every year. We are seeing more market and consumer adoption, but still. So A and C are the correct options here. Possible advantages, disadvantages, drawbacks of AM. We discussed this. Okay. So we are done with the first lecture of this week. Let us break for a couple of minutes. Maybe join again around 8:15, 8:17, and then we'll continue.
Sir, can you send the PDF, sir? This one.
Yes, Karthi, it will be available to you. The NPTEL team will share a link with the link to these documents. Yes.
Yesterday document also, sir.
No, no. So you will receive a notification from them. Maybe it'll take a couple of days, but yes, you will receive them.
Okay. Thank you, sir.
Okay. So let us take a break and meet again around, say, 8:17. Hi everyone, welcome back and let us resume. I hope my screen is visible to you. In the second lecture this week, Professor Kapil covered CAD models for additive manufacturing, and maybe something important to look at is the difference between geometry and topology. So, when you say geometry, it contains information about the dimensions, such as the lengths or the length of this arc, the radii of this arc. When you say topology, the information should also contain something about the connectivity or the interconnectedness. So, which part is connected to which other part and how? By what formal system is what is topology all about? So, a very illustrative example here. You see that these two parts are the same geometry mostly because, say, both L1 are the same in length, L2 is the same, as well as between L1 and L2, the angle again remains the same. C1 is part of the same arc, having the same radius. What is changing is actually the center here. The center of this arc lies outside, whereas in this case it lies inside. So that is changing the topology because they might have the same geometrical feature as in same dimensions of the straight lines, same length of the curve, even same radius of the arc, but because they're connected differently, their topology changes. Whereas in the example to the right, you might have similar topology again. This arc is, say, concave with respect to this body, and in both cases, the center of this arc lies outside. But as you can see that L1 here and L1 here, they're not the same. So L1 for, say, body A need not be the same as the length L1 for body B. Again, they are not also connected at the same angle. So this one here is a right angle, but this one is not 90 degrees. So something illustrative to actually distinguish between geometry and topology, even though often we use them interchangeably in a wrong sense. As we discussed in the last lecture, STL is the predominant file format for storing geometric data, especially in the context of additive manufacturing. And as we also discussed, it was derived initially from stereolithography, which was the first 3D printing technique, starting right from the 1980s. And with time, the abbreviation evolved to mean a standard tessellation language, or even sometimes a standard triangle language. Why triangle? Because triangles are the shapes mostly used for tessellation in any STL file. When you open it, you'll find. And what is tessellation in the first place? It is actually the process of covering any surface, be it rectangular, circular, or any odd shape. If you can cover this surface totally without any overlapping, so no overlap and no gap, then the surface is said to be tessellated. Do all of these tessellating units have to be the same size? No. as long as you're covering the surface. Say I have a larger rectangle here and smaller rectangles somewhere here. It's okay. What is important is that there should be no overlap and there should be no gap. No overlap between two neighboring units. So this is not allowed, and no gap. So I try to tessellate it with squares, and suddenly here I see that I can fit nothing. This remains a gap. This is not allowed. So also as formally defined, tessellation is the process of tiling a surface with one or more geometric shapes. So you can actually combine multiple shapes, maybe fill this area with a triangle, such that there are no overlaps and no gaps. STL is a boundary representation model because it only gives you the surface. It does not contain any information about the solid itself, and it uses a connected series of triangles. The triangles are connected to each other at their vertices. So they will be connected at least at one vertex, or they may be connected across more of them. As you see, to capture a geometrically intricate surface, you cannot do it with a small number of triangles. You have to opt for a larger number of smaller triangles. However, this will increase the file size and the computation. This will increase the error. So what you want is something in between, something which is optimum both for performance and size, whereas not compromising on the details or the geometrical accuracy itself. Again, why triangles? As I was showing in the previous example here, I can very well tile a surface with squares or rectangles. So why particularly triangles? There are a few key reasons for it. First is that you can define a plane by any 3 points, any three non-collinear points to be in fact. That's why, cameras have tripods. They do not have 3 feet. What is the reason? Because using these three non-collinear points, you will always be able to describe a plane. Any three non-collinear points form a triangle. It is in fact the smallest the closed polygon with the least number of sides. And every triangle forms or describes a unique plane. This is actually the most important reason why we use triangles. Points of a triangle cannot simultaneously be part of multiple planes, and thus there is no duplicacy or no ambiguity. Again, any surface can be broken down into triangles, but any surface can also be broken down into rectangles or maybe pentagons. But triangles can only be broken down into triangles. I mean, yeah, if you want to take it to an extreme, maybe you have a large rectangle here, a smaller rectangle, and you try to make the rectangle smaller and smaller and smaller. But however fine you go to fill this final area around the vertex, you need a triangle only. The equation of plane, which is enclosed by 3 points of a triangle, was illustrated by this example. We'll also cover something similar in the questions that are to come. Now, the contents of an STL file. So, what an STL file actually describes are facets, actually these small triangles that you see tessellating any surface. They carry information about these individual facets. The files lack any topological information, so strictly geometrical. And as they are represented by finite numbers, say float point digits, there can be round off errors which add up over time, compound, and finally you end up with a big error. So this point is supposed to be part of both of these triangles, but over various iterations, the coordinates get separated enough for a gap to exist here. This is because of round off errors which are used in computation. And STLs do not store information about the dimension unit. So it's just parametric information. You don't know the exact dimensions. You can scale it up or down. Among two formats used for storing STLs are the ASCII format, which is more user friendly, and the binary format, which is more computer friendly. Up here, an example of an STL file. So as we said, it describes facets. The first line will contain information about the outward normal. It's important. So any surface has two normals, one going inward, one outward. This always describes the outward normal. When I say outward, so along the direction of the normal, we will have empty space. When I go against the normal, I expect to find something. Maybe I'm going inside whatever surface this was. Now it houses a loop. In that loop, it has information about the three vertices. The order of these vertices is immaterial. I mean, this can go here, this can come here, but they should be described in a manner consistent with the right hand thumb rule. So you have three vertices. You must describe them in an anti-clockwise fashion, starting anywhere. You can start with A, B, C. You can start with B as well. It does not matter, or even with C. But what is important is the anti-clockwise order. Again, for each facet, a normal. This is for facet 1. This is for facet 2. And the information about vertices. Again, this example asks us to find the normal of a triangular facet. We'll do something similar in the upcoming exercise. The facet normal data is redundant. Why is that? Because using information from the three vertices, we can actually calculate the normal. Thus, it's not at all important for it to be described separately. Still, you can consider it a failsafe. I think this example was covered very well by Professor Kapil in class. So we will save some time here. Uh, this actually covers dividing a cubical surface into triangles. That is basically tessellating the surface. It has six faces, so it will have 12 triangles covering it, and then describing each of these facets in an STL file. So you have information about each facet in successive slides. Again, you will find that the sequence of these vertices is consistent with the right hand thumb rule. That is when I wrap my fingers around the vertices, going from this direction and here, my thumb points in the direction of the outward normal. Again, as we discussed, an STL file can also be stored in a binary format, which saves space and is more machine friendly. Uh, this slide and the successive slide contains a description of such a file format. Now, resolution. We also discussed this during slicing and yeah, somewhere in tessellation as well, that we will never end up with the exact geometry when we are tessellating it. what we can have is a good approximation, and the approximation can be as good as you want it to be. So you can keep on making it finer and finer and finer, unless, of course, the triangle actually disintegrates or collapses into just a line. So you have a triangle with a very high aspect ratio. And after a point, it becomes impossible to distinguish the two edges because this one has grown so small. So aspect ratio of the triangles plays a key role in your computational efficiency as well as accuracy. In certain cases, you might not achieve convergence at all. A coarse representation or a coarse tessellation will take less time, be computationally light, but then you are compromising on accuracy and dimensional exactness. A file tessellation, as you can see, will uh, lead to a larger file size, have a large number of triangles, be more exact, but again more heavy. What you want is an optimum somewhere in between. And this optimization is achieved by two means, by controlling either the deviation tolerance, which is expressed in terms of the chord height. So you have a curve and you tessellate it. So maybe a straight line here, another here, and so on. And this height from the actual to the sorry, this distance from the actual to the tessellated surface is your chord height. If I minimize the chord height, of course, I have better accuracy. But then again, more number of triangles, a larger file size, more computationally heavy. If I make it too large, I will not be able to capture the geometry itself. Rule of thumb is to actually keep the tolerance or the deviation tolerance between 0.01 mm to 0.001 mm. This is because these are the working ranges of most additive manufacturing machines. I mean, not DED. So if you want to print it via DED, maybe you're looking at resolutions of say 1 mm rather than 0.01. In powder bed, yeah, some micrometers. In watt photopolymerization, even less. So maybe this is achievable via a watt photopolymerization process. Even if you were to specify a value of tolerance smaller than this, your machine itself would not be able to achieve it, and thus it is pointless. An example of deviation tolerance, we'll again cover one in our exercises. And angle tolerance is actually another way of quantifying the deviation from the actual geometry to the tessellated. And it involves the angles between the outward normals of two neighboring faces which are not exactly aligned to each other. So if I have two tessellated surfaces which have parallel normals, no, I'm not looking at this case. I'm looking at cases where there is an angle between the normals. This angle dictates my angle tolerance. Another example. Now, some important topology rules with which Professor Kapil went over in his lecture. So each triangle must share two vertices with its neighboring triangle, and one vertex can be shared by as many. So at least two, and no ceiling on how many. The orientation rule, which we are discussing about. First, you indicate the direction of the normal, which should point outwards. This is the outward normal. And second, the vertices are also listed in a counterclockwise fashion, consistent with the right hand thumb rule. Each triangle should have at least one common point. This is connectivity. So no triangle can be isolated. They must be connected to the rest. And no triangle should have an intersection with the interior of any other triangle. This is consistent with the rule of tessellation, which states that there can be no gaps and no overlaps. Else you are describing the same region twice. And some of the errors, apart from the round off error that we discussed, that the computation of line of intersection of two surfaces, such as one shown here, can lead to errors in knot-to-knot connection vertex. So you have a triangle with a vertex lying very close to this line of intersection, but on what surface do you actually place that vertex? Is it on surface 1? Is it on surface 2? Or is it freely floating in air? As the round of errors continue to mount, this can become a true case. And raising the accuracy of computation may not help, as we discussed, because the triangles must have a defined aspect ratio. You can't make them too lean and too tall, because after a point, the two edges will simply degenerate and fall on top of each other, coinciding. And high degree edges can be created and shared by more triangles, particularly at tangential positions. So consider this edge over here. It is shared by two triangles in the plane. And a third one here. So especially at a certain corner or at a tangential position, this can become the case. Now we'll work out some of the example problems which are relevant to this lecture. So yeah, equation of plane. So given three vertices, say I name them A, B, and C. Can we actually find the equation of the plane that is passing through all three of these? So yes, we can. The first thing to do in this case is to check for collinearity, which will be a simple determinant. So I have 1, 2, 0, 1, 4, 2, and minus 4, 2, minus 2. If this is equal to 0, then they are collinear. If not, then we are good to proceed. So I'll just work this out. So it's not 0. So definitely the points are not collinear. They do form a triangle. And now we're supposed to find equation of the plane which is actually passing through those 3 points. So as you'll find in your slides, the formula is actually substitute the vertices where 1 is for A, 2 for B, and 3 for C. So this will give us This is the necessary equation of plane. Is uniquely contained by these 3 points. The next question is which peculiar properties of triangles make them a suitable choice for tessellation? We discussed them. So all of the above clearly. And here I put an example where they're tiling a surface with greater polygons. So here you have an example of pentagons. However, if you start tiling with regular pentagons, what you'll observe is a gap here. But if you go with shaped pentagons, you can actually tile a surface, like on the example to the right. And it is mathematically proven that all triangles tessellate, all quadrilaterals tessellate, a few pentagons tessellate. So there are 15 types, a few hexagons as well. There are known at least three. These are the only three. Pentagons, more can find out. And any polygon with sides of 7 or more do not tessellate. It is a mathematically established fact. This next example involves finding the unit vector of a facet from the vertex information. So let's do it. So again, I'm just naming these three vertices as A, B, and C. And here is my triangle. The way to find the normal is that, say, any two vectors, such as A, B in this case, this vector right here, with its head here, and AC, their cross product will be normal to the plane containing this triangle. And if I am to divide it by its magnitude, I will end up with a normal vector, which is a unit normal vector. So first, let's find these vectors AB and AC. So AB is just so the position vector of B minus the position vector of A. So something like this. So these notations represent vectors, as you might be aware. These ordered pairs are for the I, J, and K components. So what I have is 0, 2, 2. This translates to 0 I cap plus 2 J cap plus 2 K cap for vector AB. Similarly, for vector AC, I have position vector of C minus position vector of A, which is minus 5, 0, and minus 2. This corresponds to minus 5 I cap plus 0 J cap minus 2 K cap. Now, I want a cross product. So, this is a vector cross product. So, as you'll remember from your mathematics classes, and then expanding, I have minus 4 I cap minus 10 J cap plus 10 K cap. So, this is a normal vector, but it's not a unit normal. So I divide it by its magnitude. And your unit normal is, of course, it is possible to simplify this further, which you guys can do. This is the unit normal vector required in this case. The next question talks about the STL file format and what information it does not contain. So it was mentioned in the slide that it does not contain information about the topology. Does it contain information about the material? Will someone volunteer, please? So nowhere did we speak about any material or any information regarding material that can be contained in STL. It just gives a geometrical description of the surface, that to an approximate description. So material is not contained. Similarly, no texture and no color. So none of this information is actually contained by an STL file. But as I said, STL is an old file format. Have there been any advancements? So yes, we have the OBJ file format, which is basically short for object. It contains information about the geometry, of course, as well as about the color and texture. This can be supplied in the form of a companion PNG file, that is a separate PNG, or even a material template library. Another more recent file format is AMF, also sometimes 3MF, which is the additive manufacturing file format. It is XML based and highly customizable, and it includes a lot of data such as 3D surface geometry, color, materials, lattices, textures, and constellations also. It does use triangular meshes just like STL. However, the triangles can be curved. So rather than just straight triangles trying to fit along a curve, maybe you have a curved triangle, which gives you a more accurate fit. Here I have included an example to actually demonstrate the difference in file sizes as well as the extra information such as color or material which is contained in an AMF file format. This is a numerical for deviation tolerance. So how many triangles are required for a deviation tolerance to be 0.01 mm and the representation of a circle of 10 mm radius. So as we discussed, let this be our circle. I am drawing these lines just to give myself some reference and say it is tessellated by these triangles. And I have a neighboring triangle here. And it is this deviation tolerance which is supplied to me. What I'm trying to determine is how many such triangles can I divide or tessellate the surface into. So say you have n triangles and you're dividing this 360 degrees into n. So each of this individual angle is actually 360 by n or 2 pi by n. Again, this normal is exactly halfway through, so it's an angle bisector. So either one of this is pi by n. Again, when you are checking for neighboring triangles, pi by n and pi by n will give you 2 pi by n again. And if you look at one individual triangle, this length is r. This angle, as we discussed, is pi by n, and this is the deviation tolerance given to us. So mathematically, this can be represented as we'll also find in the slides that this distance, if d is nothing but the radius minus the component of the neighboring radius, so the cosine is the distance itself, or so you just collect terms, substitute values. So the radius is 10 mm, sorry, and the right hand side is 0.01. So this will give me 1 minus cos pi by n shall equal 0.001. So cos pi by n in this case is, yeah, so it's 0.999, and this will allow you to find the value of n. I do not have a calculator at the moment, but yeah, this is the final step. You find the cos, arc cos or the cos inverse, and this will give you n. Angle tolerance, similar. So in the interest of time, I'm not solving it. So that brings me to the end of this session. If you guys have any feedback or any suggestions or any further doubts, please feel free to ask. If not, we'll close this session. Thank you. Thank you for coming to the first session, first live session of Fundamentals of Additive Manufacturing Technologies. I am Saurav from IIT Bombay. Thank you.